300 million years after creation began, something appeared that should not exist. Massive galaxies, already assembled, already shining, already organized like cities in the cosmic dark. The James Webb Telescope opened its golden eyes and saw them everywhere. Galaxies that break our timeline, objects glowing too bright, structures too mature for an infant universe. Headlines screamed that cosmology was shattered. Scientists questioned decades of work, but here's what actually happened in the deepest corners of space. If you enjoy this journey through cosmic mystery, hit that like button and subscribe. We're diving into the impossible. Take a breath. We launch into answers that challenge everything. Summer 2022. Astrophysicist Erica Nelson stared at her screen and froze. Bright red spots scattered across the darkness. Objects invisible to Hubble. Galaxies so distant their light traveled over 13 billion years. Light from when the universe was barely 300 million years old. Every model predicted these galaxies should be tiny, chaotic, barely formed clumps struggling to ignite. Instead, Nelson saw massive structures, organized systems, galaxies looking mature as our own Milky Way, yet existing when the cosmos was still an infant. The University of Texas team measured 6 objects. Each weighed more than 10 billion times our closest star's mass. One appeared heavier than the Milky Way itself. Our galaxy had nearly 14 billion years to grow, pulling in gas, birthing countless generations of stars, developing its spiral arms. These ancient galaxies had only 300 million years, a fraction of the time. Yet there they were, already giants. The discovery sent shockwaves through astronomy worldwide. Richard Ellis at University College London called them monsters, appearing in the very first images. Garth Illingworth from UC Santa Cruz said observations sat way outside the box of what models predicted. These weren't minor discrepancies where numbers were slightly off. These were fundamental contradictions that challenged decades of theoretical work. Standard cosmology follows a straightforward rule. Galaxies form gradually over cosmic time. Dark matter creates invisible scaffolding across space. This scaffolding slowly captures hydrogen and helium gas from the surrounding universe. Over hundreds of millions of years, that gas compresses under the relentless pull of gravity. Eventually, it reaches densities and temperatures where nuclear fusion ignites. Stars are born. The process takes time, lots of time. Webb's targets formed almost instantly by cosmic standards. To grow so massive so quickly, these galaxies would need to convert nearly 100% of their available gas into stars. That efficiency breaks known physics. Typically, only 10% of gas becomes stars. The rest gets blown away by powerful stellar winds or remains unconverted in the spaces between stars. 100% conversion sits right at the theoretical edge of possibility. It would require something to be very different from what we expect. Some scientists proposed radical explanations. Maybe the universe expanded faster shortly after the Big Bang than our equations predict. That would require new forces we haven't discovered, new particles we haven't detected, a complete rewrite of fundamental physics. Others suggested our galaxy formation models needed major revision. Perhaps stars formed differently in the early universe. Perhaps we fundamentally misunderstood how efficiently ancient clouds could collapse and ignite. Nelson and colleagues published their findings in the journal Nature Astronomy. The paper carried a stark message. Either something was very wrong with our understanding of how galaxies form, or something was very wrong with cosmology itself. Those massive early galaxies were just the beginning. Webb acts as a cosmic time machine. The concept seems impossible at first, a machine that looks backward through billions of years of history. Yet that's exactly what happens every single time we observe distant regions of space. Light travels incredibly fast, about 186,000 miles per second. Nothing in the universe moves faster, but the universe itself is unimaginably vast. Distances between objects span millions, billions, even trillions of miles. When you look at a star located 100 light-years away, you're seeing light that left that star 100 years ago. You're observing it as it existed in the past, not as it is right now in this present moment. The farther across space you look, but deeper backward through time you travel. Webb was built specifically to exploit this fundamental principle of astronomy. Its 18 mirror segments, each one plated in pure gold, work together to gather infrared light from the most distant corners of the observable universe. Not the visible light our human eyes can detect. Infrared light, electromagnetic radiation with longer wavelengths that exists just beyond the red end of the visible spectrum. This design choice was deliberate and absolutely crucial to the telescope's primary mission. When light travels across billions of years through continuously expanding space, something remarkable happens to it. The expansion of the universe itself stretches the light. Imagine pulling on both ends of a spring. The coils get farther apart. The wavelengths of light behave similarly. They stretch longer. Visible light shifts progressively toward the red end of the spectrum, then beyond into infrared. Astronomers call this phenomenon redshift. The farther away an object sits from us, the more its light has been stretched during the long journey across expanding space. Hubble Space Telescope observes primarily in visible light wavelengths. It can detect some infrared radiation, though that's not its specialty. It's not optimized for those longer wavelengths. This limitation meant Hubble could only see so far back through cosmic time. Beyond a certain distance, ancient galaxies became effectively invisible to its instruments. Their light had redshifted completely out of the visible range that Hubble was designed to capture. Enter Webb. Nancy Levinson, director of the Space Telescope Science Institute that operates these telescopes, explains that Webb was specifically designed to see what Hubble simply couldn't. Those incredibly ancient galaxies, whose light now arrives at Earth as infrared radiation, Webb collects that ancient infrared light and translates it into detailed images scientists can study. Astronomers use the letter Z to denote redshift values in their calculations. Higher Z means farther away, means looking deeper into the past. Hubble could spot galaxies with redshift values around 11. That was its practical limit. Webb started finding galaxies with redshift values of 13, 14, even 16. Some candidate objects possibly reached redshift 20. Each incremental jump in redshift represents hundreds of millions of additional years deeper into cosmic history. This capability transformed They calculate how many galaxies should exist at different distances from Earth. They estimate how bright those galaxies should appear when we observe them. These predictions aren't wild guesses. They come from decades of careful observations, tested physics theories, and sophisticated mathematics. The predictions said early galaxies should be faint, small, struggling to shine through the dense fog of neutral hydrogen that filled all of space back then. Webb should barely be able to detect them, even with its incredible sensitivity and advanced technology. Reality looked completely different. The galaxies blazed with unexpected intensity. They shone dramatically, impossibly brighter than any predictions allowed. At the University of Missouri, astronomer Haojing Yan led a research team that identified 300 candidate galaxies from the early universe. All of them glowed brighter than they should according to every model. All of them defied straightforward explanation. The brightness problem connects directly to the mass problem discussed earlier. Bright galaxies contain enormous numbers of stars. Lots of stars require lots of mass. Lots of mass takes substantial time to accumulate through gravitational attraction. Time these particular galaxies simply didn't have available. Consider the timeline carefully. The Big Bang happened 13.8 billion years ago according to our best measurements. Webb found these problematic galaxies existing just 300 to 700 million years after that initial moment. That proportionally short time span is like finding a fully grown adult human 20 minutes after conception. The required development happened impossibly fast by any reasonable standard. Scientists ran sophisticated computer simulations trying to reproduce what Webb actually observed. They tweaked various variables in their models. They adjusted multiple parameters. Some simulations could produce massive early galaxies matching observations, though only under very specific, finely tuned conditions. Those required conditions demanded the universe involved massive star formation bursts. Maybe these ancient galaxies were experiencing explosive periods of stellar birth unlike anything in the modern universe. Imagine a galaxy creating millions of stars simultaneously instead of the steady trickle of formation seen in present-day galaxies. That concentrated burst could potentially explain the extreme brightness. Another possibility seemed even stranger and more exotic. Perhaps much of the brightness came from supermassive black holes rather than stars. Active black holes can outshine their entire host galaxies as they violently devour surrounding matter. University of Colorado researchers examined the spectroscopic data carefully. They found most unexpectedly bright objects were indeed galaxies producing starlight. Real stellar populations were generating most of the brightness. The star formation efficiency problem was genuine and unavoidable. Gas doesn't easily transform into stars. The process involves immense gravitational pressure, precisely correct temperature conditions, and incredibly complex physics occurring across vast scales. In modern galaxies we can study today, astronomers observe that about 10% of available gas eventually becomes stars. The remaining 90% escapes the system or remains unconverted. That 10% figure isn't some arbitrary number pulled from thin air. It reflects genuine physical limitations imposed by the laws of nature. As stars begin forming from collapsing gas clouds, they immediately start generating intense stellar winds that blow outward in all directions. These powerful winds physically push away the surrounding gas that might otherwise fall inward to create more stars. Young stars also emit copious amounts of radiation that heats nearby material to temperatures where gravity can no longer easily compress it into additional stars. This natural feedback loop inevitably limits how efficiently any given region can produce stars. The early massive galaxies Webb discovered would have needed to operate at 90 to 100% efficiency to match observations. Nearly all their available gas would have needed to successfully become stars. This efficiency level is theoretically possible under extremely specialized edge cases in physics models. However, it shouldn't be the normal mode of operation. It definitely shouldn't characterize every massive galaxy in the early universe simultaneously. Mike Boylan-Colchin at the University of Texas led a research team carefully analyzing this efficiency puzzle. His group calculated exactly how efficient star formation processes needed to be to create the massive galaxies Webb was observing. The mathematical results were striking and undeniable. These galaxies would need to be converting almost every single available atom of hydrogen and helium gas into stellar material. No waste, no loss, no significant amounts of gas blown away by the stellar feedback that dominates modern galaxies. This situation created as much of a philosophical problem as a scientific one. The early universe was supposed to be fundamentally messier than the universe today, less organized, more chaotic. Young galaxies should be relatively inefficient at their tasks. They should be fumbling their way through star formation, learning as they go. They shouldn't be executing the process with near perfect efficiency from the very beginning. Some researchers proposed that environmental conditions in the early universe were simply dramatically different from today's universe. Maybe the gas was substantially denser throughout all of space. Maybe the absence of heavy elements fundamentally changed how clouds could collapse. Heavy elements like carbon, nitrogen, and oxygen help cool gas clouds through radiation, making them easier to compress under gravity. The very first galaxies had almost no heavy elements whatsoever, since those only form inside stars. Perhaps This pristine composition actually enabled more efficient star formation through mechanisms scientists don't yet fully understand. Others suggested the distribution of dark matter was different in the early universe. Dark matter provides the gravitational wells where normal matter collects to eventually form galaxies. If dark matter was more concentrated in the early universe for some reason, it could have pulled gas together far more effectively than it does today. This would naturally create the higher densities that might enable more efficient star formation. The puzzle remained stubbornly unsolved despite intensive theoretical work. Among all the genuinely strange objects Webb discovered in its surveys, one particular class stood out as especially bizarre and unexplained. Astronomers started informally calling them little red dots. The name sounds almost cute and innocent. The reality underlying these objects is anything but simple. Little red dots are exactly what their name suggests: compact sources that glow intensely red in Webb's infrared images. They're remarkably tiny, much smaller than typical galaxies we observe. Yet somehow they shine with incredible luminosity that shouldn't be possible for objects their size. They appear in surprisingly huge numbers around 600 million years after the Big Bang. Then, mysteriously, about 1.5 billion years later, they essentially vanish from the cosmic record. We no longer see them at later times. Where did these objects originally come from? Where did they ultimately go? What fundamental nature are they? Nobody knows for certain, despite considerable investigation and speculation. Scientists have proposed theories ranging from relatively conventional to wildly exotic. Maybe they're actually normal galaxies, undergoing unusually explosive star formation episodes, somehow compressed into extraordinarily small volumes of space. Maybe they're supermassive black holes, surrounded by extremely thick cocoons of dust that absorb direct light and re-emit it as infrared. Maybe they represent something entirely new that we've simply never encountered before in astronomical observations. The little red dots challenge our understanding in multiple independent ways. First, there are far too many of them appearing in Webb's images. Statistical models based on galaxy formation theory predict much fewer such objects should exist at those distances. Second, they're impossibly compact given their distances. Normal galaxies at similar distances should appear more spatially extended and diffuse when we observe them. Third, their spectral signatures remain frustratingly ambiguous. The detailed characteristics of light they emit doesn't clearly match pure stellar populations or pure black hole emissions or any other single known astrophysical source. Some researchers suggested these little red dots might represent quasars embedded in dense cocoons. Quasars are extraordinarily active supermassive black holes that blast enormous amounts of radiation across the entire electromagnetic spectrum. If such a violently active black hole was deeply embedded in an extremely thick envelope of dust surrounding it, that dust would absorb most of the ultraviolet and optical light. The heated dust would then re-radiate all that absorbed energy in the infrared part of the spectrum. From our distant perspective on Earth, this physical setup would appear as a compact red source matching basic observations. However, this quasar cocoon explanation struggled significantly with the abundance issue. To produce so many quasar cocoons appearing in Webb's relatively small survey areas, you'd need supermassive black holes to be extraordinarily common in the early universe. Much more common than any formation theory predicts. That requires those black holes to somehow form and grow very quickly immediately after the Big Bang. Other scientists proposed more exotic and speculative explanations. Perhaps little red dots actually represent matter-antimatter annihilation events occurring in the early universe. When matter and antimatter particles meet, they mutually destroy each other in intense flashes of pure energy. This idea remains highly speculative and currently lacks any real supporting evidence. Perhaps strangest of all is the little red dot's mysterious disappearance. By approximately 2 billion years after the Big Bang, they're almost completely absent from observations. What happened to them all? Did they evolve into normal galaxies through some transformation process? Did they simply fade away because whatever exotic process powered them exhausted its fuel source? One particular little red dot proved stranger than all the rest. One specific galaxy carries a name drawn from ancient poetry, Virgil. Located at a distance corresponding to 800 million years after the Big Bang occurred. At first glance, through standard observations, it appears perfectly ordinary, completely normal when astronomers view it in visible and ultraviolet light wavelengths. Then you switch to infrared wavelengths and examine those observations. Everything changes dramatically. Virgil transforms before your eyes. The galaxy appears to explode in brightness when viewed through infrared instruments. What initially seemed like a modest collection of stars suddenly becomes a blazing beacon of energy. Astronomers at the University of Arizona quickly realized something genuinely extraordinary was happening with this object. This wasn't simply another distant galaxy. It was a cosmic Jekyll and Hyde transformation. Virgil holds the distinction of being the single reddest object in the entire little red dot population Webb has discovered. It's dramatically redder than even other red objects. Spectacularly, off the charts redder in ways that immediately suggested something highly unusual must be generating that extreme infrared emission. The research team pointed Webb's mid-infrared instrument directly at Virgil for extended observation periods. What those observations revealed genuinely shocked everyone who examined the data. Virgil contains a supermassive black hole that's actively devouring surrounding material at an extraordinary rate. The black hole is accreting matter at rates far exceeding what should be physically possible for a galaxy of its measured size and mass. That's actually not the most shocking part of the discovery. Plenty of distant galaxies harbor active black holes busily consuming gas and dust. The truly shocking aspect is the mass ratio. The black hole appears to be growing substantially faster than its host galaxy is growing, much faster. The black hole has somehow gotten ahead in the cosmic race. In all standard models of galaxy and black hole evolution, these two components are supposed to grow together over time. They should maintain relatively constant mass relationships. More massive galaxies predictably have proportionally more massive black holes sitting at their centers. This tight correlation has been carefully observed and measured across billions of years of cosmic history in countless galaxies. Virgil comprehensively breaks that fundamental rule. Its central black hole got way ahead of its surrounding galaxy, like a marathon runner who inexplicably left their running companion miles and miles behind. This strongly suggests that supermassive black holes don't necessarily wait patiently for their host galaxies to catch up in mass. They can apparently grow independently through their own processes. Perhaps they even form before their surrounding galaxies have finished fully assembling. The discovery carries profound implications for understanding cosmic structure formation. If black holes can significantly outpace galaxy formation processes, then all our detailed models of how these structures grow together over time are fundamentally incomplete. Perhaps black holes actually form first in the early universe, then subsequently use their immense gravity and tremendous energy output to directly influence how surrounding gas eventually forms into stars and galaxies. Virgil's supermassive black hole is thoroughly shrouded in thick layers of dust. This dust efficiently absorbs the intense ultraviolet and optical radiation streaming from the accretion disk of superheated material spiraling into the black hole. The heated dust then re-emits all that absorbed energy as longer wavelength infrared light. That's precisely why Virgil looks completely normal in visible light wavelengths yet explodes dramatically in infrared observations. The dust acts like a cosmic filter, completely hiding the true monster within from casual observation. The sheer amount of dust surrounding Virgil is itself highly unusual and demands explanation. Cosmic dust forms primarily from heavy elements created deep inside stars through nuclear fusion. When those stars eventually die, especially in violent supernova explosions, they scatter those newly created elements into surrounding space. Over many successive generations of stars, living and dying, enough heavy elements gradually accumulate in a region to create significant amounts of dust. However, Virgil exists only 800 million years after the Big Bang. There simply shouldn't have been enough time for many stellar generations to live complete lifetimes and die. There shouldn't be substantial amounts of dust anywhere yet. Yet Virgil is absolutely choked with dust in quantities that shouldn't exist. Virgil earned its poetic name because it guides us into completely unknown territory. The relationship between supermassive black holes and their host galaxies has always appeared to be a kind of cosmic partnership in astronomy. Two distinct components growing together over billions of years of time, each one significantly influencing the evolution of the other. A balanced gravitational dance of matter and energy. Webb's observations are systematically revealing that this comfortable picture might be completely wrong. Supermassive black holes sit at the centers of most large galaxies throughout the universe, including our own Milky Way. These aren't the relatively small stellar mass black holes that form when individual massive stars collapse at the ends of their lives. These are genuine monsters, containing millions or even billions of times our star's mass compressed into incredibly small volumes. Their ultimate origins remain deeply mysterious to astrophysicists. For many decades, astronomers carefully observed and measured a remarkably consistent pattern. The mass of any galaxy's central black hole correlates very tightly with various properties of that host galaxy itself. Bigger galaxies predictably have proportionally bigger black holes at their centers. This relationship is so mathematically regular and tight that it strongly suggests genuine coevolution over time. As galaxies steadily grow larger by accumulating gas and merging with neighboring galaxies, their central black holes also grow larger through accreting material and merging with other black holes. This standard paradigm firmly assumed that galaxies must form first, or at absolute minimum, that galaxies and their central black holes grow together in perfect lockstep throughout cosmic history. Webb's systematic observations are thoroughly shattering this comfortable assumption. Across multiple independent studies examining different samples, astronomers repeatedly find supermassive black holes in very early galaxies that are far too massive for their relatively small host galaxies. The black holes somehow got significantly ahead. At the University of Arizona, researchers carefully studying the unusual galaxy Virgil reached a striking conclusion. Black holes actually get ahead of their host galaxies in many cases throughout the early universe. They explicitly called this the single most exciting finding from all their work. It fundamentally suggests the causality might actually run backwards from everything we previously thought. Maybe black holes don't passively form inside already existing galaxies. Maybe supermassive black holes actually form first in the early universe and then actively influence exactly how galaxies subsequently assemble around them. This radical idea isn't completely unprecedented or new. Some theoretical astrophysicists have previously proposed that black holes could potentially act as seeds for galaxy formation. A sufficiently large black hole naturally creates an extremely deep gravitational well in space around itself. This well inevitably attracts gas from the surrounding region. The gas falls toward the black hole, though most of it doesn't fall directly in. Instead, it settles into stable orbits, gradually forming a rotating disk. Within this gas disk, material can cool, compress under gravity, and eventually form stars through familiar processes. If this alternative scenario is actually correct, then black holes aren't merely consequences of galaxy formation, they're primary causes of it. The black hole comes first. The visible galaxy we observe is secondary and derivative. Webb found confirmed supermassive black holes in galaxies as early as 290 million years after the Big Bang itself. That's barely enough time for virtually anything to form, let alone supermassive black holes already containing millions of stellar masses. How do you possibly create a black hole with 1 million times our star's mass in less than 300 million years? Either many smaller stellar mass black holes must merge together with implausibly high efficiency, or the very first black holes somehow started much larger than we thought possible. The first option requires merger rates far higher than any realistic models predict. The second option demands entirely new formation mechanisms that physics doesn't currently understand. Regardless of the specific formation mechanism, early supermassive black holes had profound effects on their surroundings. Active black holes emit absolutely enormous amounts of energy. The questions multiply faster than credible answers. Early in 2025, Webb delivered yet another discovery that left astronomers staring at their computer screens in genuine disbelief. A massive spiral galaxy displaying beautiful, well-defined spiral arms, crystal clear structure, organized rotation, the kind of elegant form typically seen only in mature galaxies that are billions of years old. Except this particular galaxy existed within just the first 2 billion years of the universe. The discovery team named it the Big Wheel. The name perfectly captures both its size and distinctive shape. Spiral galaxies are extremely common in today's universe. Our own Milky Way is one. The famous Andromeda Galaxy is another. These elegant structures form when a galaxy has sufficient time to settle down into a stable rotating disk. Gas spirals gracefully inward along sweeping arms. Stars form continuously within these arms, creating the brilliant patterns visible in photographs. The entire process requires stability, time, relatively calm conditions for the disk to organize itself properly. The early universe was anything except calm. It was fundamentally chaotic. Galaxies formed primarily through violent mergers. Small clumps smashed together repeatedly. Material flew in from all directions. The universal expectation was that early massive galaxies should be elliptical, roughly blob-shaped, smooth and essentially featureless, definitely not elegant spirals. Dr. Themia Nanayakara at Swinburne University of Technology in Australia was one of the key researchers who discovered the Big Wheel. He explained that finding such a massive early galaxy with clear spiral structure is deeply interesting and puzzling. You would naturally expect something that large existing that early to be elliptical based on all formation theories. There are essentially two possible explanations. Either the Big Wheel somehow grew exceptionally large without experiencing the violent mergers that should be common, allowing it to maintain organized rotational structure throughout. Or, alternatively, most of its stellar mass formed in situ. In situ specifically means the stars formed directly within the galaxy itself, rather than being brought in from other galaxies through mergers. The first option requires truly exceptional circumstances. For any galaxy to successfully avoid major mergers while simultaneously growing so large, it would need to exist in a relatively empty region of space. However, massive galaxies typically form in crowded regions, where dark matter is highly concentrated. These are precisely the same regions where mergers should be extremely common. The Big Wheel somehow avoided this apparently universal fate. The second option suggests extraordinarily efficient star formation happening within a stable rotating disk. The galaxy would need to pull in gas very smoothly from its surroundings, have that gas settle into a disk, then convert it into stars at high rates without significantly disrupting the disk structure. This seems difficult to explain given the turbulent conditions in the early universe. The Big Wheel measures roughly comparable to the Milky Way in total mass. Our galaxy had over 13 billion years to reach its current size and develop its distinctive spiral structure. The Big Wheel accomplished similar development in a small fraction of that time. Spiral structure also requires specific physics to maintain. The arms aren't rigid features painted on the disk. They're actually density waves that propagate through the disk over time. Stars and gas move in and out of the arms as they orbit the galactic center. The arms persist because the wave pattern is stable. Creating and maintaining these waves requires precisely correct gravitational conditions and gas distribution. Too much turbulence disrupts them. Too many mergers completely destroy them. The big wheel's discovery strongly suggests that at least some early galaxies achieved remarkable stability much sooner than any predictions. This has significant implications for understanding the overall evolution of cosmic structure. If stable disks could form early, perhaps the transition from the chaotic early universe to the organized modern universe happened more quickly than anyone thought. Additional Webb observations are actively planned to search for more early spiral galaxies. Either way, the big wheel's mere existence seriously challenges narratives that early galaxies were uniformly chaotic. Strange discoveries kept accumulating. The University of Missouri research team thought they were conducting a straightforward survey, map out distant galaxies using Webb's powerful cameras, build a comprehensive census of the early universe. Standard astronomical work. What they found instead was an entire population of objects that simply shouldn't exist according to all theories. 300 candidate galaxies, all of them shining brighter than predictions allowed, all of them from the early universe, all of them completely defying explanation. Haojing Yan led the project. His team used two of Webb's sophisticated infrared cameras, the near-infrared camera and the mid-infrared instrument. Both are specifically designed to detect light from the most distant parts of space. To identify these early galaxy candidates, the researchers used an established method called the dropout technique. This method cleverly exploits how light from distant objects gets absorbed by intervening hydrogen gas. Neutral hydrogen atoms efficiently absorb ultraviolet light at specific characteristic wavelengths. When you look at a very distant galaxy, any ultraviolet light it emits gets progressively absorbed by hydrogen clouds between us and that galaxy. This creates a distinctive pattern in the galaxy's spectrum. It appears to drop out at certain wavelengths. By carefully measuring which wavelengths are missing, astronomers can estimate how far away a galaxy is. The more hydrogen absorption, the more space the light has traveled through, the farther away the galaxy must be. But the 300 objects the team identified were all unexpectedly bright. Not slightly brighter, far brighter. Bright enough to seriously question whether standard galaxy formation models work at all. If even a small fraction of these objects turn out to be what the team thinks, current ideas about how galaxies formed in the early universe will need major revision. That's a direct quote from Yan. The uncertainty is real. Confirming distances and properties requires follow-up observations. Some might be foreground objects misidentified as distant galaxies. Some might be unusual astrophysical phenomena mimicking distant galaxy signatures. Some might have distances overestimated. However, even if only 50 or 100 turn out genuine, the problem remains. The brightness problem compounds other issues. These objects aren't just massive, they're luminous. They're actively forming stars, or harboring active black holes, or doing something energetic, producing copious light. The team noted most high redshift surveys might be missing similar objects. Many surveys use relatively shallow observations in mid-infrared wavelengths due to time constraints. If you only observe briefly, you only detect very brightest objects. There could be thousands more slightly fainter objects that surveys miss. This connects to the Virgil discovery. Many surveys are optimized to find objects bright in near-infrared, yet don't look deeply in mid-infrared. This bias means dust-obscured galaxies and active black holes might be systematically undercounted. Understanding these 300 objects requires spectroscopic follow-up. Webb can obtain detailed spectra revealing chemical composition, gas motions, and other properties. Several large programs are underway doing exactly this. Early results show most candidates do appear to be genuine distant galaxies. The confirmation rate is high. This is both exciting and troubling. Exciting because Webb succeeds at its primary mission. Troubling because discrepancies with theoretical predictions are real. The 300 objects are part of larger patterns. Everywhere Webb looks in the early universe, it finds more galaxies than expected, brighter galaxies, more massive galaxies. The discrepancies aren't localized. They're everywhere. This suggests the problem isn't with individual observations. The problem is systematic. Either our instruments are consistently wrong, which seems unlikely given careful calibration efforts, or our theories are missing something fundamental about the early universe. After the Big Bang, the universe wasn't transparent like it is today. It was filled with thick fog, not water droplet fog like Earth experiences, fog of neutral hydrogen atoms. These atoms absorbed ultraviolet light efficiently. Any energetic photon trying to travel through space would quickly be captured. The universe was dark, opaque, a cosmic prison for light. This period is called the epoch of reionization. Reionization means hydrogen was ionized, transformed from neutral atoms into separate protons and electrons. This transformation made the universe transparent. Light could finally travel freely. Standard models predict reionization occurred between about 400 million and 1 billion years after the Big Bang. First stars and galaxies produced intense ultraviolet radiation. This radiation slowly ionized surrounding hydrogen. Over hundreds of millions of years, bubbles of clear space expanded around galaxies. Eventually the bubbles merged. The fog disappeared. The process should have been gradual. During reionization, galaxies trapped inside fog shouldn't send certain light types out to us. Specifically, they shouldn't show Lyman alpha emission. Lyman alpha is characteristic wavelength of light produced when electrons in hydrogen atoms drop from higher to lower energy levels. It's bright and easy to detect. It's also easily absorbed by neutral hydrogen. If galaxies are surrounded by neutral hydrogen fog, any Lyman alpha light produced gets absorbed within short distances. We shouldn't see it. The fog blocks it completely. Only after fog clears around galaxies can Lyman alpha photons escape into intergalactic space and eventually reach our telescopes. Webb found a galaxy called JADES GS 131. This galaxy exists only 330 million years after the Big Bang, deep in the reionization epoch, deep in fog. It should not show Lyman alpha emission. The fog should block it. It shows Lyman alpha emission. Bright, clear, unmistakable. The fog lifted around this galaxy far earlier than models predicted. Roberto Maiolino from University of Cambridge called the result totally unexpected. Standard theories of early galaxy formation suggested this was impossible. The galaxy is seen when the universe was only 330 million years old. Surrounding fog should be thick, impenetrable. Yet the telltale signature of Lyman alpha shines through as if fog isn't there. How could this happen? Several possibilities exist, none simple. First, maybe this particular galaxy existed inside an unusually large bubble of ionized space. Perhaps the region around it had already been cleared by earlier stars or galaxies. This would require other luminous sources nearby that aren't visible in current observations. Second, maybe the galaxy itself is extraordinarily powerful. Perhaps it's producing so much ultraviolet radiation it cleared fog around itself in small regions. This would require intense star formation or active black holes. The energy output would need to be extreme to ionize hydrogen across light years of space in such short time. Third, maybe our models of reionization are wrong. Perhaps the process happened faster than thought. Perhaps regions of space became transparent earlier than predicted. This would require revising understanding of how efficiently early sources produced ionizing radiation and how quickly that radiation could clear hydrogen fog. A fourth possibility involves fog structure itself. Maybe it wasn't uniform. Maybe neutral hydrogen was clumpy, thick in some regions, thin in others. If this galaxy happened to exist in naturally thinner regions, Lyman alpha photons might escape more easily. This still requires explaining why that region was thinner. The discovery suggests reionization was more complex than simple gradual clearing. It might have been patchy, variable, some regions clearing quickly while others remained fogged. This patchiness could explain why some early galaxies show Lyman alpha while others don't. The team studied the galaxy's spectrum carefully. Lyman alpha is single emission line at specific wavelength. If they were seeing different spectral features misidentified as Lyman alpha, that would explain the anomaly without requiring weird physics. Detailed analysis confirmed identification. The emission line is definitely Lyman alpha. The galaxy is definitely at indicated distance. The fog should definitely be blocking this light, yet here it is. Additional observations of other early galaxies are ongoing. Scientists want to know if this galaxy is unique. The answer will determine if the entire reionization story needs revision. 3 galaxies stand out even among all unusual objects Webb discovered. Astronomers call them the red monsters. The name fits perfectly. They're enormous. They're red from extreme redshift, and they defy every model of how galaxies should form. An international team led by University of Geneva found them. Each of the 3 red monsters is nearly as massive as the Milky Way. Each existed with her. Over time, stars form. The process is limited by physics. Only about 20% of captured gas or less actually becomes stars. The rest escapes or remains unconverted. The red monsters broke these limitations. They converted much more gas into stars, possibly 50%, maybe more. This efficiency level challenges fundamental assumptions about galaxy formation. Why were these 3 galaxies so much better at making stars than everything else? One possibility is they existed in unusually dense regions of early universe. If dark matter halos were exceptionally concentrated, they would create deeper gravitational wells. These wells could capture and hold gas more effectively. Less gas would escape. More would be available for star formation. Another possibility involves the gas itself. First gas in universe was almost pure hydrogen and helium. No heavy elements. Heavy elements form inside stars and get scattered when stars die. Very first galaxies worked with pristine material. Maybe this pristine gas behaved differently. Maybe it cooled and collapsed more efficiently. A third idea focuses on mergers. If red monsters formed through numerous mergers of smaller galaxies, each merger would bring fresh gas. It would also trigger star formation bursts. Repeated mergers could maintain high star formation rates over extended periods. Garth Illingworth, emeritus professor at UC Santa Cruz, worked on Webb for decades during development. He called the red monsters remarkable and said they pose real conundrums. The existence of such massive galaxies at earliest times contradicts expectations about how structure grows. The team used Webb's spectroscopic capabilities to measure accurate distances and stellar masses. Spectroscopy splits light into component wavelengths. This reveals detailed information about chemical composition, gas motions, star formation rates, and other properties. The FRESCO survey provided data. Most sources in FRESCO fit existing models reasonably well. The red monsters were outliers. 3 out of hundreds examined, but 3 is enough to indicate real phenomena rather than measurement errors. The researchers calculated red monsters formed stars nearly twice as efficiently as lower mass counterparts and as later galaxies. This factor of 2 difference doesn't sound enormous, but it's enough to push them across lines from possible to problematic. Standard models can accommodate modest variations in efficiency. They struggle with systematic differences of this magnitude. Future observations with Webb and ground-based telescopes will provide further insights. The team plans to study these ultra-massive red monsters in more depth. They also hope to find larger samples of similar sources. If red monsters are part of broader population, understanding them becomes even more critical. The researchers concluded these galaxies will offer new insights into conditions that shaped universe's earliest epochs. This is scientific understatement. The red monsters don't just offer insights. They demand revision of fundamental theories, and they're not the only structures that appeared organized too early in cosmic history. The defining expectation for early galaxies was simplicity, disorder, chaos. Small clumps of stars barely held together by gravity, irregular shapes, turbulent gas, active merging. Everything messy and unfinished because there hadn't been time for organization to develop. Webb's observations show the opposite. Many early galaxies look mature, organized, structured. They have defined shapes, clear components, evidence of settled stellar populations. They look like galaxies that evolved for billions of years, not hundreds of millions. This maturity appears in multiple forms. Some early galaxies, like the Big Wheel, have spiral structure. Others show smooth elliptical forms. Still others contain distinct bulges and disk components. These features all indicate organization levels that take time to develop. Consider what must happen for galaxies to look mature. First, you need lots of stars. Star formation isn't instantaneous. Even in ideal conditions, turning gas clouds into stars takes millions of years. Building populations of billions or trillions of stars requires sustained formation over long periods. Second, you need chemical evolution. First stars are made of hydrogen and helium. When they die, they create heavier elements: oxygen, carbon, iron, dozens of others. These elements get incorporated into next-generation stars. Over successive generations, metallicity increases. The ratio of heavy elements to hydrogen grows. Mature galaxies show evidence of multiple stellar populations with different metallicities. This indicates generations of stars have lived and died. Elements have been created, scattered, and incorporated into new stars. The chemical record preserves history of star formation. Seeing this record in galaxies only a few 100 million years old is startling. Third, you need dynamical settling. When galaxies first form through mergers of smaller clumps, motions are chaotic. Stars orbit in random directions. Gas clouds collide. Everything is turbulent. Over time, these motions settle down. Orbits become organized. Gas settles into rotating disks. Spiral structure can form. This dynamical evolution takes time. Interactions between stars and gas gradually drain energy from random motions and convert it into organized rotation. The Cambridge team studied over 250 early galaxies discovered by Webb. They found most were turbulent gas-filled systems rather than stable disks. This was closer to expectations, but significant minorities showed signs of organization, enough to indicate at least some early galaxies achieved maturity quickly. The mature galaxy paradox isn't just about appearance, it's about timescales. The universe has finite age. Webb observes it at specific moments in history. Light travel time sets absolute limits on how much evolution could have occurred. A galaxy seen at 500 million years after Big Bang has only had 500 million years to evolve, period, no exceptions. Within that time, galaxies had to form from initial density fluctuations, accumulate gas, ignite first stars, experience multiple generations of stellar evolution, develop chemical enrichment, undergo numerous mergers, settle into stable structures, and establish mature appearances we observe. That's enormous evolution compressed into tiny time window. Some processes can be accelerated under extreme conditions. Intense star formation can proceed rapidly if gas densities are high. Mergers can happen quickly if galaxies are close together, but there are limits. Stars have finite lifetimes. The most massive stars, which die quickly and produce heavy elements, still live for at least a few million years. Chemical evolution has minimum timescales set by stellar physics. The mature galaxy paradox suggests either we're misunderstanding something about timescales, or conditions in early universe were dramatically different from today in ways that accelerated evolution. Neither option is comfortable. The first requires questioning fundamental physics. The second requires explaining why early universe was so different and why those conditions changed. Some researchers propose what we interpret as maturity might be illusion. Perhaps these galaxies look mature actually aren't. Maybe light is dominated by a few very bright stars creating misleading impressions. Maybe unusual gas conditions mimic spectral signatures of evolved stellar populations. These explanations require complex scenarios and remain speculative. The maturity of early galaxies remains one of Webb's most philosophically troubling discoveries. For decades, cosmologists built sophisticated computer models. These simulations started with initial conditions set by observations of cosmic microwave background. They evolved forward in time, following physics laws. Gravity pulled matter together. Dark matter formed halos. Gas cooled and collapsed. Stars ignited. Galaxies assembled. The models produced detailed predictions about what early universe should look like. The predictions were clear. Early galaxies should be small, faint, irregular, chaotic. They should grow gradually through mergers and accretion. By 500 million years after Big Bang, largest galaxies might contain a few billion stellar masses. Most would be much smaller. Brightest would shine with modest luminosity compared to modern galaxies. Structure would be minimal. Webb turned on and immediately contradicted these predictions. The early universe is bright, crowded, full of massive galaxies. Many show organized structure. The discrepancy isn't subtle. It's dramatic. The models were not slightly wrong. They were fundamentally wrong about state of early universe. How did sophisticated models built by brilliant scientists using decades of observational constraints fail so completely? One reason is models rely on assumptions. Some assumptions come from observations. Others come from theoretical physics. Still others are pragmatic choices made because full calculations would be too complex. Each assumption is reasonable individually, but small errors compound. If several assumptions are slightly wrong in same direction, final result can be very wrong. For example, models assume certain star formation efficiency rates based on observations of nearby galaxies. Maybe those rates don't apply to early universe. Models assume dark matter halos have particular density profiles. Maybe those profiles were different early on. Models assume initial density fluctuations follow specific statistical patterns. Maybe patterns had unexpected features. Another factor is computational limitations. Even largest supercomputers can't simulate entire universe at high resolution. Scientists must choose what to include and what to approximate. They simulate representative volumes of space and extrapolate to larger scales. They model individual galaxies in detail, yet approximate surrounding environment. These choices inevitably introduce errors. A third issue involves feedback processes. When stars form, they affect environments. Stellar winds blow gas around. Supernova explosions heat material and drive shocks. Radiation pressure pushes on dust grains. Black holes pump energy into surrounding gas. All these feedback processes regulate star formation. Too little feedback and galaxies form stars too efficiently. Too much feedback and star formation gets suppressed. Getting balance right is incredibly difficult. The models predicted moderate feedback that would limit early galaxy growth. Webb suggests feedback was weaker or different. This allowed early galaxies to form stars more efficiently and grow more massive more quickly. Understanding why requires understanding microphysics of how radiation interacts with gas, how stellar winds propagate, how supernova energy couples to surrounding medium. These are complex problems, spanning orders of magnitude in scale from individual stars to entire galaxies. Cosmologists are now revising models frantically. They're adjusting parameters, adding new physics, exploring different assumptions. The goal is to reproduce what Webb observes while maintaining consistency with other constraints. This is harder than it sounds. You can't just tweak one number to fix one problem. The models are interconnected webs of physics. Changing one thing affects everything else. Some revised models can now produce massive early galaxies by increasing star formation efficiency in early universe. This works to match observations, but it raises new questions. Why was efficiency higher then? What physical processes drove differences? How and when did conditions transition to lower efficiency seen in modern galaxies? Other models focus on initial conditions. Maybe density fluctuations from Big Bang were slightly larger than we thought. This would seed faster structure growth. Regions would collapse sooner. Galaxies would form earlier. This approach can match some observations yet struggles with others. It also requires explaining why our measurements of cosmic microwave background don't show larger fluctuations. The confrontation between predictions and reality is humbling. It reminds us even our best models are approximations. The universe is under no obligation to behave as equations predict. When observations contradict theory, observations win, always. The job of theorists is to figure out why, and contradictions Webb revealed run even deeper. The universe didn't start perfectly smooth. Immediately after Big Bang, tiny variations existed, quantum fluctuations in space-time fabric itself. Some regions were infinitesimally denser than others. These differences were incredibly small, 1 part in 100,000, but over time, gravity amplified them. Denser regions attracted more matter. Smaller fluctuations take longer. The universe remains smooth for extended periods before significant structure develops. We've measured these initial fluctuations precisely. Satellites like COBE, WMAP, and Planck mapped cosmic microwave background radiation. This is light from 380,000 years after Big Bang. Temperature variations in this radiation directly reflect density fluctuations present at that time. The measurements are excellent. The fluctuations are small, exactly 1 part in 100,000, just as theory predicted. Given these measured fluctuations, calculations show how fast structure should grow. You start with observed ripples. You apply gravity. You track how matter clumps together over time. The math is straightforward. The results are clear. By 500 million years after Big Bang, you should have modest clumps, small proto-galaxies, nothing massive, certainly nothing organized. Webb found massive organized galaxies, many of them, everywhere it looked. This suggests either fluctuations were larger than we measured, or gravity worked differently than we thought, or some other process accelerated structure formation beyond what standard physics predicts. The first option seems ruled out. Cosmic microwave background measurements are incredibly precise. Multiple independent satellites agree. The fluctuations are definitely small. You can't make them bigger without contradicting firm observational constraints. Any model that requires larger initial fluctuations immediately conflicts with microwave background data. The second option involves modifying gravity. Perhaps Einstein's general relativity doesn't work perfectly on cosmic scales. Perhaps there are correction terms that become important in early universe. Modified gravity theories exist. Some can accelerate structure formation, but most have problems. They conflict with other observations. They require fine-tuning. They make predictions that don't match reality in differences of cold particles that only interact through gravity. But what if dark matter has other properties? What if it interacts with itself in subtle ways? These interactions could change how dark matter halos form and evolve. They might allow structure to develop faster. Another idea focuses on baryonic matter. In early universe, baryonic matter was almost entirely hydrogen and helium gas. This gas had to cool before it could collapse and form stars. The cooling rate depends on gas composition and presence of molecules that can radiate energy. If early gas cooled more efficiently than models assume, it could collapse faster. This would accelerate galaxy formation. A third possibility involves feedback working differently. Usually, feedback from stars and black holes suppresses galaxy growth, but under certain conditions, feedback might trigger growth instead. Imagine supernova shock waves compressing nearby gas. If conditions are right, that compression could trigger rapid star formation rather than dispersing gas. This positive feedback could drive explosive galaxy growth. Researchers at Johns Hopkins and UT Austin tested whether changing early density fluctuations could explain massive galaxies. They calculated how much change would be needed. Then they checked what else such changes would affect. The problem was that making more massive galaxies also meant making many more smaller galaxies. But Hubble's observations of smaller galaxies didn't show predicted increases. The numbers didn't match. This suggested standard cosmological model might still be okay. The issue might lie elsewhere. The density fluctuation problem remains unsolved. Something allowed structure to form faster than standard physics predicts. The epoch of reionization transformed universe from opaque to transparent. Before reionization, neutral hydrogen fog filled space. After reionization, that fog was gone, ionized into separate protons and electrons. Light could travel freely. The cosmos became clear void we observe today. Standard models predict reionization occurred between 400 million and 1 billion years after Big Bang. Massive stars in early galaxies produced intense ultraviolet radiation. This radiation ionized surrounding hydrogen. Bubbles of clear space expanded around each galaxy. Eventually, bubbles merged. Last neutral hydrogen disappeared. Reionization was complete. The process should have been gradual. First galaxies appeared around 200 to 400 million years. They started ionizing immediate surroundings. Over next several hundred million years, more galaxies formed. More ultraviolet radiation flooded space. Ionized bubbles grew and merged. By 1 billion years, job was done. This timeline made sense. It matched theoretical predictions. It aligned with indirect observational evidence. Webb is revealing different story. Reionization might have happened faster, started earlier, proceeded more efficiently than models predicted. The evidence comes from multiple sources, all pointing in same direction. First, Webb found numerous dwarf galaxies in reionization epoch. Dwarf galaxies are small, much less massive than giant galaxies. Previous surveys missed most because they're faint. Webb's sensitivity allows detection of previously invisible objects. Teams counting dwarf galaxies found they outnumber massive galaxies by about 100 to 1. This ratio is much higher than expected. Why does this matter? Dwarf galaxies produce ultraviolet radiation too. If there are 100 times more dwarf galaxies than thought, there's much more ionizing radiation available. More radiation means faster reionization. The cosmic fog clears sooner. Hakim Atek from Sorbonne University led study analyzing these dwarf galaxies. His team used gravitational lensing to magnify distant objects. Massive galaxy clusters act as cosmic magnifying glasses. They bend space around them. This bending focuses light from background galaxies, making them appear brighter and larger. By observing through these natural telescopes, astronomers can detect incredibly faint objects. The team studied dwarf galaxy population carefully. They measured how much ultraviolet radiation these small galaxies produce. The results were clear. Dwarf galaxies provided most photons that reionized universe. Not massive galaxies. The little guys did heavy lifting. This finding changes our understanding of reionization fundamentally. Previous models focused on massive galaxies as primary ionizing sources. Those models predicted slower reionization timeline because massive galaxies take longer to form. If dwarf galaxies did most work, they could have started earlier and proceeded faster. Second evidence comes from Lyman alpha detections discussed earlier. Finding Lyman alpha emission from galaxies at 330 million years suggests fog was already clearing around some objects. This is earlier than standard timelines predict. If multiple galaxies show similar signatures, it indicates widespread early clearing. Third, Webb discovered surprisingly mature galaxies existing during reionization. Mature galaxies require multiple generations of stars. First generation produces ultraviolet radiation that ionizes local gas. Subsequent generations form in partially cleared regions. Seeing mature galaxies during reionization suggests process was well underway earlier than thought. The galaxies had time to evolve because reionization started sooner. The new picture of reionization is more complex than old one. Instead of simple inside-out process where bubbles slowly expand and merge, reionization might have been patchy and variable. Some regions cleared quickly. Others remained fogged longer. The dwarf galaxies, numerous and widespread, created countless small ionized bubbles. These bubbles overlapped in complicated patterns. The patchiness explains some of Webb's observations. Why some early galaxies show Lyman alpha while others don't? Why ionization signatures appear at different times in different locations? The universe wasn't reionizing uniformly, it was reionizing chaotically. This matters for understanding galaxy formation. The state of surrounding gas affects how galaxies grow. Neutral gas behaves differently than ionized gas. It cools differently, collapses differently, forms stars differently. If reionization happened earlier and more variably, it would have influenced galaxy evolution in ways previous models didn't account for. The Penn State team that discovered dwarf galaxy population noted findings provide clearest picture yet of very low-mass newborn galaxies created less than billion years after Big Bang. These tiny galaxies are central to cosmic origin story. They did more than anyone realized, but even accounting for faster reionization doesn't solve all problems Webb uncovered. The cosmological model scientists use has a name: Lambda CDM. Lambda represents dark energy, the mysterious force accelerating universe's expansion. CDM stands for cold dark matter, the invisible matter providing gravitational structure. The model includes normal matter too: protons, neutrons, electrons, the stuff we're made of. Together these components describe cosmic evolution from Big Bang to present. Lambda CDM has been remarkably successful. It explains cosmic microwave background patterns, the abundance of light elements, the large-scale structure of universe, galaxy distributions, cluster properties. The model has passed test after test. It's standard paradigm for a reason. It works. But models are only as good as their weakest assumption. Lambda CDM assumes certain things. Dark matter exists and behaves in specific ways. Dark energy exists and affects expansion in specific ways. General relativity correctly describes gravity on cosmic scales. The universe started from hot, dense conditions. These assumptions all have support, but they're still assumptions. Webb's observations stress Lambda CDM. They don't clearly break it, but they push against predictions in uncomfortable ways. This prompts questions. Should we modify model, or should we trust model and revise our understanding of processes within it? Testing model means checking predictions against observations systematically. Identify what model predicts for specific observables. Measure those observables carefully. Compare. If predictions and measurements agree, model passes. If they disagree, either model is wrong or our understanding of how to connect model predictions to observations is incomplete. The massive early galaxies test Lambda CDM's structure formation predictions. The model predicts how matter clumps over time, how dark matter halos form, how much mass they contain at different epochs. From these predictions, you can estimate how massive galaxies should be at early times. The estimates depend on assumptions about star formation efficiency and feedback. But even being generous with those assumptions, Lambda CDM struggles to produce most massive galaxies Webb observes. One approach to testing model involves simulations. Run hundreds or thousands of simulated universes, starting from Lambda CDM initial conditions. Evolve each one forward in time. Track galaxy formation. Build statistics. See if extreme objects Webb finds fall within expected range of outcomes. If even most extreme simulated galaxies are smaller than observed ones, model has problems. If rare simulations produce similar galaxies, model might be okay. The observed galaxies would just be statistical flukes, unlikely but possible. Several groups performed these simulations. Results are mixed. Some simulations can produce massive early galaxies under specific conditions, others can't. The disagreement stems from different implementation details, how feedback is modeled, how star formation is treated, what resolution is used. These technical choices affect outcomes significantly. Higher resolution simulations can track smaller structures. They resolve finer details, but they're computationally expensive. Lower resolution simulations are cheaper, but they miss physics happening at small scales. Different groups make different trade-offs. This creates variation in results. Eventually, as computational power increases, these differences should narrow. For now, uncertainty remains. Another test involves cosmic microwave background. This radiation comes from when the universe was 380,000 years old. It encodes information about conditions at that time. Lambda CDM makes precise predictions about microwave background patterns. Satellites measured these patterns exquisitely. The agreement between predictions and observations is excellent. This strongly supports Lambda CDM's description of early universe. But what if model is right about very early universe and wrong about later times? What if something changed? Perhaps dark energy wasn't constant. Perhaps its strength varied over cosmic history. This would alter expansion rates. Changing expansion affects structure, growth timelines. Maybe faster early expansion could allow rapid early galaxy formation. Modified dark energy models exist. Quintessence models replace cosmological constant with dynamic scalar fields. This field can vary over time and space. If quintessence had different properties in early universe, it could potentially explain some Webb observations. But these models introduce free parameters. They're less constrained than Lambda CDM. They can be tuned to fit almost anything. Testing modified dark energy requires multiple independent observations. Measure expansion history. Study structure growth. Examine how galaxies cluster. Look at how light from distant objects is distorted by intervening matter. All these tests constrain dark energy properties. Current consensus is Lambda CDM probably doesn't need modification at fundamental level. The model's basic structure appears sound. What might need modification is our understanding of baryonic physics, how gas cools, how stars form, how feedback operates. These processes occur within Lambda CDM framework. Getting them right is crucial for predicting galaxy properties. The universe is expanding. This fact is settled. Galaxies recede from each other. Space itself grows larger over time. The rate of expansion is described by Hubble constant. This number tells you how fast universe is expanding right now. It's measured in kilometers per second per megaparsec. For every megaparsec of distance, expansion adds certain velocity. Measuring Hubble constant precisely has been goal for decades. Different methods give slightly different answers. This discrepancy is called Hubble tension. Some measurements using cosmic microwave background give values around 67. Other measurements using nearby supernovae give values around 73. The difference is small in absolute terms, but it's larger than measurement uncertainties. Both methods should give same answer. They don't. This is troubling. What does this have to do with Webb's massive early galaxies? The expansion rate affects cosmic timelines. Faster expansion means universe expands more in given time. Structures have less time to form before being pulled apart by expansion. Slower expansion gives more time. If expansion rate in early universe was different from what we think, it could affect when galaxies formed and how quickly they assembled. Some researchers proposed early universe expanded faster than standard lambda CDM predicts. This would require additional physics, new forces or particles that operated during first few 100 million years. These would accelerate expansion temporarily. Then they would shut off. The universe would transition to standard expansion we see in later epochs. Why would this help? Faster early expansion seems like it would make problem worse. Less time for structure to form. Galaxies should be smaller, not larger, but situation is subtle. Faster expansion changes relationship between observable redshift and actual cosmic time. A galaxy at certain redshift would be observed at earlier time than in standard models. If massive galaxies exist at that redshift, it means they formed even earlier than we thought. This strains models more, not less. Unless expansion rate affects structure formation in non-obvious ways, perhaps faster expansion in certain phases could actually enhance structure growth under specific conditions. The mathematics gets complicated. Different effects pull in different directions. Without detailed calculations, intuition can mislead. Mike Boylan-Kolchin and his team considered whether varying expansion rate could explain massive galaxies. They concluded simple modifications don't work. To produce what Webb observes through expansion rate, changes alone requires extreme modifications. The early universe would need to expand several times faster than predicted. This creates conflicts with other observations. The cosmic microwave background. Light element abundances. Multiple constraints rule out such large changes. Small modifications remain possible. Perhaps expansion rate was 10 or 20% different. This wouldn't conflict with most observations, but it also wouldn't solve galaxy mass problem. You'd need to invoke other mechanisms too. Modified expansion plus high star formation efficiency plus unusual stellar populations. The explanation becomes complicated. Occam's razor suggests simpler alternatives might be better. The Hubble tension itself might provide clues. If tension is real and not due to systematic errors, it indicates something about cosmic expansion we don't understand. Perhaps expansion rate evolved differently than lambda CDM predicts. Perhaps there's physics missing from model. If so, this missing physics might also affect early structure formation. Solving Hubble tension and explaining massive early galaxies might be connected. Several theoretical proposals attempt to address both issues simultaneously. These involve modifications to dark energy properties, or additional components in cosmic energy budget, or changes to how radiation and matter couple in early universe. The ideas are speculative. They require testing against multiple datasets. Webb will contribute measurements that help constrain these proposals. One approach measures distances to objects at various redshifts. By comparing observed brightness to intrinsic luminosity, you can infer distance. Do this for many objects at many redshifts. Map out expansion history. See if it matches lambda CDM predictions or deviates. Webb can observe objects at high redshifts where other telescopes struggle. This extends expansion history measurements to earlier times. Another approach uses gravitational lensing. Massive structures bend light from background objects. The amount of bending depends on mass distribution and geometry of space. The geometry is set by expansion history. By carefully measuring lensing effects, you can constrain expansion parameters. Webb's sharp imaging enables precise lensing measurements. These tests will take time, years of observations, careful analysis, cross-checks with other data. Gradually picture will clarify. Either expansion rate is standard and galaxy formation is unusual. or expansion rate is modified, and that helps explain galaxies. The expansion rate question highlights how interconnected cosmology is. Every parameter affects every prediction. The universe builds from small to large. This hierarchical growth principle underlies modern cosmology. Tiny fluctuations grow into small structures. Small structures merge into bigger ones. Bigger ones combine into larger ones still. Over billions of years, this process creates cosmic web, galaxies, clusters, superclusters, the grand architecture of universe. Evidence for hierarchical growth is strong. We observe ongoing mergers between galaxies. We see evidence of past mergers in galaxy morphologies, tidal streams of stars, disrupted satellite galaxies, asymmetric structures indicating recent collisions. The modern universe clearly operates hierarchically. Simulations predict this process extends back to beginning. First structures were small, perhaps just millions of masses. These merged into larger clumps containing tens of millions, then hundreds of millions, eventually billions. The process is bottom up. Small structures form first. Large structures come later. This prediction is fundamental to lambda CDM. The model works because it naturally produces hierarchical growth. Dark matter clumps in self-similar way across many scales. Larger structures form from smaller ones through gravity. The mathematics is elegant. The physics is straightforward. Webb's observations challenge this picture. Early massive galaxies look like they formed top-down instead of bottom-up. They're already large, already organized, already massive. Where are intermediate stages? Where are numerous small proto-galaxies that should have merged to create these giants? The dwarf galaxy population exists. Webb finds lots of small galaxies, but ratio of large to small seems off. There should be thousands of dwarfs for every massive galaxy if hierarchical growth operates as predicted. Webb finds hundreds. Still a lot, but not thousands. The numbers don't quite match. Moreover, massive galaxies don't show strong evidence of recent major mergers. They're not train wrecks. They're not obviously assembled from distinct components. Some have smooth morphologies. Others have organized structures like spiral arms. These features suggest relatively calm formation histories, not violent merger-driven assembly that hierarchical growth predicts. This doesn't mean hierarchical growth is wrong. It means process might have operated differently in early universe than it does today. Perhaps mergers were less disruptive. Perhaps galaxies could merge and quickly settle back into organized states. Perhaps rapid star formation during mergers obscures merger signatures. Or perhaps some massive galaxies formed through different mechanisms. Instead of building up through mergers, they might have grown through smooth accretion. Gas streaming steadily from surrounding space, settling into disk, forming stars. This in situ formation produces organized structures without requiring violent mergers. Evidence for in situ formation comes from several sources. The Big Wheel galaxy with spiral structure suggests smooth accretion. Violent mergers destroy spiral arms. If Big Wheel grew primarily through accretion rather than mergers, its spiral structure makes sense. But accretion-based growth should be slower than merger-driven growth. How did Big Wheel accumulate so much mass so quickly through smooth processes? The answer might involve those cold streams mentioned earlier. Dark matter filaments channel gas toward halo centers. The gas remains cold. It doesn't shock heat. It penetrates straight to galaxy. This delivers fuel for star formation efficiently. If cold streams were particularly effective in early universe, they could enable rapid smooth growth without mergers. Why would cold streams be more effective early? Perhaps because universe was denser, filaments were shorter, gas didn't have to travel as far, it didn't heat up as much. The streams stayed cold over larger scales. This would boost accretion rates significantly. Another factor involves feedback. In modern galaxies, star formation and black hole activity heat gas and blow it away. This suppresses further growth. In early universe, maybe feedback was weaker. Gas wasn't expelled as efficiently. It stayed in galaxy. More turned into stars. This would enable faster growth even without enhanced accretion. Testing hierarchical growth requires observations of galaxy morphologies over cosmic time. Webb excels at this. Its resolution reveals structures in distant galaxies Hubble couldn't see clearly. Teams are classifying thousands of Webb-discovered galaxies, looking at shapes, identifying mergers, measuring asymmetries, building statistics on what fraction are disturbed versus relaxed. Early results show diversity. Some early galaxies are disturbed train wrecks. Others are surprisingly smooth. The distribution might differ from later cosmic epochs. But exactly how and why remains under investigation. More data will clarify trends. The hierarchical growth paradigm won't be abandoned easily. Too much evidence supports it, but it might need refinement. Perhaps growth is more hierarchical at later times and more mixed early on. Perhaps both bottom-up mergers and smooth accretion contribute. The relative importance of different processes might vary across cosmic history. Understanding this matters for making sense of galaxy evolution throughout time. Cosmic dawn marks when first stars ignited. Before this moment, universe contained no light except fading glow of Big Bang itself. After cosmic dawn, stars began to shine. Light flooded space for first time. This transition from darkness to light defines an epoch, the moment when creation truly began. When did cosmic dawn occur? Standard models predicted around 200 to 400 million years after Big Bang. Before then, gas was too diffuse, too hot, not ready to collapse into stars. Cooling took time. Condensation took time. The first stars couldn't form immediately. They had to wait for conditions to ripen. Webb is pushing cosmic dawn earlier. The telescope finds luminous objects from just 200 to 300 million years. These aren't just first feeble stars. They're vigorous star-forming galaxies, bright sources, active systems. For these to exist at 290 million years, first stars must have formed even earlier, maybe 150 to 200 million years, maybe sooner. How early could stars possibly form? There's theoretical limit. Gas must cool from millions of degrees down to temperatures where molecular hydrogen can form. Molecules help gas collapse. Without them, star formation is difficult. Cooling takes time even under ideal conditions. Estimates suggest 100 million years minimum, maybe less under extraordinary circumstances, but not much less. If cosmic dawn happened at 150 million years, we're getting close to theoretical limit. If it happened earlier, we need to understand what accelerated process. What made gas cool faster? What enabled collapse sooner? These questions probe fundamental physics of early universe. One possibility involves first, dark matter halos. These form from initial density fluctuations. Bigger fluctuations collapse sooner. If fluctuations were slightly larger than we think, halos would form earlier. Gas would fall into them earlier. Stars would ignite earlier. This is same idea discussed regarding galaxy masses. Bigger, early fluctuations solve multiple problems, but they conflict with cosmic microwave background observations. Another idea focuses on molecular hydrogen formation. This requires bringing two hydrogen atoms together under right conditions. In diffuse primordial gas, molecular formation is rare, but in slightly denser regions, it happens faster. If early dark matter halos created sufficient density enhancement, they might have accelerated molecular hydrogen formation dramatically. This would enable earlier cooling and earlier star formation. The first stars themselves might have helped. Once a few stars ignited, their ultraviolet radiation would ionize surrounding hydrogen. But farther away, radiation wasn't strong enough to ionize. Instead, it just excited hydrogen atoms into higher energy states. When these excited atoms de-excited, they released specific wavelengths of light. This light could pump more molecular hydrogen formation through a process called indirect cooling. The first stars would make it easier for subsequent stars to form nearby. This self-accelerating process could drive explosion of early star formation. Start with a few stars. They make more molecular hydrogen possible. More stars form. These make even more molecular hydrogen possible. The process snowballs. Within tens of millions of years, you go from isolated stars to vigorous star-forming regions. This could compress cosmic dawn into brief, intense period rather than gradual, drawn-out process. Evidence for early cosmic dawn comes from multiple Webb observations, the numerous massive galaxies at high redshifts, the unexpected Lyman alpha emission from extremely distant sources, the mature stellar populations in galaxies only a few 100 million years old. All these point towards star formation starting very early and proceeding very efficiently. The implications extend beyond just timing. If cosmic dawn happened early, first stars influenced universe sooner. They began producing heavy elements earlier. They started ionizing cosmic fog earlier. They seeded enrichment that eventually allowed planets and life. Pushing cosmic dawn back means universe became interesting faster than we thought. It also means our concept of dark ages needs revision. Dark ages are period between cosmic microwave background emission and first stars. A time of darkness, no light except fading afterglow of creation. Standard models gave dark ages several 100 million years duration. If cosmic dawn came at 150 million years, dark ages lasted only half as long. Less time for universe to sit in darkness, more time spent illuminated. This might seem like minor adjustment. It's not. Dark ages set stage for everything after. During this period, density fluctuations grew. Dark matter halos formed. Seeds of future structure developed. How long this takes matters. Shorter dark age means faster structure growth. Less time for small fluctuations to amplify before star formation begins. This affects whole evolutionary trajectory. Webb can't directly observe cosmic dawn. Very first stars are too distant and too faint even for Webb's incredible sensitivity, but Webb sees immediate aftermath. First galaxies those stars assembled into. By finding and characterizing these objects, astronomers constrain when and how cosmic dawn happened. The data accumulates, the picture clarifies. We're learning when lights first turned on, and answer seems to be earlier than anyone expected. Science doesn't advance through single dramatic discoveries. It advances through accumulation, multiple teams making independent observations, different methods reaching similar conclusions, contradictions getting resolved through better data. Gradually, consensus emerges or doesn't. Either way, process reveals truth. The question of whether Webb's observations break Big Bang has been investigated by dozens of research groups. Each approached problem differently. Each reached slightly different conclusions. Together, their work paints a complex picture. No simple answer exists. The situation is nuanced. Several early papers claimed massive galaxies couldn't exist within lambda CDM. These papers calculated what model predicted for early galaxy masses. They compared to Webb observations. The discrepancy was enormous, factors of 10 or more. Authors concluded model needed revision, perhaps major revision. Headlines amplified these claims. Social media exploded. Then follow-up studies arrived. These papers pointed out problems with initial calculations. Early papers had made certain assumptions that turned out incorrect. They assumed all bright objects were purely stellar. They assumed star formation efficiency was standard. They assumed simple stellar populations. When these assumptions were relaxed, conclusions changed. Papers using spectroscopic follow-up, a few outliers remained problematic. 3 or 4 galaxies couldn't be easily explained. Their masses were too high. their formation too early. No plausible combination of assumptions made them fit comfortably. Were these outliers measurement errors? Unlikely. Spectroscopic data were solid. Redshifts were secure. Masses well constrained. If measurements were correct, galaxies were genuine problems. But maybe there were unusual circumstances. Maybe these specific galaxies formed in rare, overdense regions. Maybe they represented statistical flukes. Cosmological models make probabilistic predictions. Rare events should occasionally occur. Finding a few extreme outliers doesn't necessarily break model. Statistical papers analyzed overall galaxy population. How many galaxies exist at different masses and distances? Does distribution match lambda CDM predictions? These studies found high mass end of distribution was overpopulated compared to predictions. More massive galaxies than expected, but effect was only 2 or 3 sigma. Statistically significant, but not overwhelming, possibly explainable by uncertainties in modeling. Theoretical papers explored what modifications might help. Could changing star formation efficiency by factor of 2 explain observations? Could revising feedback implementations work? Could assumptions about initial conditions be adjusted within observational constraints? These papers showed moderate modifications to baryonic physics within lambda CDM framework could potentially explain most observations. Radical changes weren't necessary. Fine-tuning was sufficient. But fine-tuning troubles some scientists philosophically. If you have to adjust multiple parameters precisely to match observations, it suggests model might be missing something fundamental. A complete model shouldn't require extensive tuning. It should naturally produce correct predictions with minimal adjustments. The fact that explaining Webb's observations under CDM remained best overall framework even if it needed refinement in specific areas. The community debated vigorously. Conferences featured heated discussions. Papers rebutted each other. Critics pointed out flaws in analyses. Authors defended their methods. This is normal scientific discourse. Messy, sometimes contentious, but ultimately productive. Through this process, understanding deepens. Current consensus, circa 2025, holds lambda CDM probably doesn't need fundamental revision. The Big Bang framework remains intact. The expansion of universe is real. The timeline is correct. Basic structure of cosmology stands. However, our understanding of galaxy formation requires significant updates. How quickly galaxies assembled, how efficiently they formed stars, how their structure developed. These processes operated differently than models predicted. This conclusion satisfies most scientists while disappointing others. The Big Bang survived, but it's been stressed and tested in unprecedented ways. The debate continues. New papers appear monthly. After years of analysis, thousands of papers, and countless debates, what do astronomers actually think about Webb's discoveries? What's real scientific conclusion stripped of hype and headlines? The Big Bang happened. This is not in question. The universe expanded from hot, dense state approximately 13.8 billion years ago. Multiple independent lines of evidence support this conclusion. The cosmic microwave background, the abundance of light elements, the redshifts of distant galaxies, the expansion of space. Webb's observations don't challenge these fundamentals. They complicate our understanding of what happened after Big Bang, but they don't invalidate Big Bang itself. Galaxies formed earlier and faster than predicted. This is clear message from Webb. Standard models underestimated how quickly structure could assemble. They underestimated how massive early galaxies could become. They underestimated how organized early galaxies could be. These are significant problems for galaxy formation theory, but they're not problems for cosmology. The distinction matters. Cosmology describes universe's overall evolution, its expansion, its composition, its geometry, its age. These things are well established. Galaxy formation is more detailed. It involves complex physics, gas dynamics, star formation, feedback. These processes are harder to model. Getting them wrong doesn't mean cosmic framework is wrong. It means detailed implementation needs work. Star formation efficiency in early universe was higher than in modern galaxies. This conclusion emerges from multiple studies. Whether efficiency reached 40% or 100% remains debated, but clearly it exceeded 10%, typical of today. Understanding why requires better modeling of primordial gas physics, how it cooled, how it collapsed, how feedback operated in metal-free environments. Supermassive black holes formed earlier and grew faster than expected. This finding comes from spectroscopic studies showing active black holes in very early galaxies. These black holes are too massive for their host galaxies. They grew ahead of galaxies somehow, either through unusually efficient accretion or through formation mechanisms that produced large initial masses. Both possibilities require new physics, or at least new understanding of known physics. Reionization might have proceeded differently than models predicted. Dwarf galaxies appear to have contributed more to reionization than previously thought. The process might have been patchier, more variable across space. This doesn't change when reionization completed, but it changes story of how it happened. More objects participated. The process was more complex. The cosmic microwave background observations remain valid and constraining. This point is emphasized in many papers. Whatever explains Webb's observations must remain consistent with microwave background data. That data pins down initial conditions precisely. You can't change early universe significantly without conflicting with that constraint. Solutions must work within this boundary. Lambda CDM cosmology is probably correct. Most scientists have reached this conclusion. The model's predictions for cosmic microwave background are spectacularly accurate. Its predictions for large-scale structure match observations. Its framework explains expansion history. Dark energy and dark matter are almost certainly real. The basic model works. Baryonic physics needs revision. This is where modifications are needed. How gas behaves, how stars form, how feedback regulates star formation. These processes are complicated. Models made simplifying assumptions. Those assumptions were too simple. More sophisticated treatments are required. This is technical work, difficult computational challenges, but not revolutionary new physics. Some mysteries remain unsolved. Little red dots don't have definitive explanations yet. The mechanism that allowed some galaxies to form spiral structure so early is unclear. The exact origin of supermassive black holes is unknown. These are open questions, active research topics. Answers will come with more data and better models. Scientists emphasize this situation is normal. Cosmology is a data-driven field. When new telescopes provide better data, they reveal phenomena that weren't predicted. This is how science advances. Theories get tested. When they fail to predict accurately, they get modified. The modifications preserve what worked while fixing what didn't. This isn't crisis, it's progress. The Big Bang theory has been tested more thoroughly now than ever before. Webb provided observations spanning from earliest epochs through intermediate times to recent past. The timeline holds up. The expansion holds up. The framework is solid, but details need work. Lots of work. That work will occupy researchers for decades. Public communication about these results has been challenging. Headlines screaming about Big Bang being broken get attention. Nuanced discussions about star formation efficiency don't. Scientists worry that sensational coverage misleads people, makes them think cosmology is in crisis when it's actually thriving, makes them doubt established science when they should appreciate how science refines understanding. The actual conclusion is simultaneously exciting and reassuring. Exciting because Webb revealed unexpected phenomena, galaxies forming faster than imagined, black holes growing sooner than predicted, structure assembling in surprising ways. These discoveries will drive research for years, reassuring because fundamental framework survived. The Big Bang happened, the universe expanded. The timeline is right. We understand cosmic history in broad strokes, even if we're still working out details. That's what scientists actually concluded. Not revolution, evolution. Not overturning cosmology, refining it. Not breaking Big Bang, completing it. Webb has been operating for over 3 years. It will continue for many more. The telescope was designed to function for at least 10 years, possibly 20 if fuel reserves last. Every day it observes, it gathers data. Every observation adds to our understanding. The discoveries so far are just beginning. Several major observation programs are underway or planned. Deep field surveys will map larger areas of sky than initial observations covered. These surveys will find more early galaxies, build better statistics, determine whether unusual objects Webb has found are rare exceptions or common occurrences. Sample size matters in astronomy. 10 weird galaxies might be flukes. 100 weird galaxies indicate real phenomenon. Thousands would demand complete revision of models. Spectroscopic campaigns will obtain detailed spectra for hundreds of high redshift galaxy candidates, confirm their distances, measure their properties, characterize their stellar populations, map their gas content. These observations take time. Webb can only observe one target at time in high-resolution spectroscopy mode. Building large samples requires patience and careful scheduling, but data will be transformative. Time-domain observations will monitor variable objects over months or years. Some early galaxies might host transient phenomena, supernovae from first stars, flares from accreting black holes, variable star formation rates. By watching these objects change, astronomers can learn about physics driving them. One snapshot shows structure. Time series show processes. Deep mid-infrared observations will search for dust-obscured objects like Virgil. Most surveys used relatively short mid-infrared exposures because instrument requires long integration times for faint sources. Dedicated mid-infrared campaigns will observe specific fields for dozens of hours. This will reveal hidden population of dust-shrouded galaxies and active black holes. How large is this population? Are there hundreds of objects like Virgil? Thousands? The answer matters for understanding early black hole growth and galaxy evolution. Gravitational lensing observations will use massive galaxy clusters to magnify distant objects. Nature provides cosmic telescopes. Clusters bend space around them. This bending acts like lens, focusing and amplifying light from background galaxies. By observing through these natural lenses, Webb can see objects far too faint to detect directly. Some of most distant galaxies ever found came from lensing surveys. Future lensing programs will push distance record farther. How far back can Webb see? The telescope was designed to find galaxies from 200 million years after Big Bang. It's already achieved that goal. Could it see farther? Maybe. If extremely luminous objects existed earlier, Webb might detect them. Population, 3 stars, if they were massive enough and formed in clusters, might be visible as very distant point sources. Finding these first stars would be monumental. Collaborative observations with ground-based telescopes will provide complementary data. Webb excels at infrared imaging and spectroscopy. Ground telescopes with large mirrors excel at collecting light and achieving high spectral resolution. Together, they can characterize objects more completely than either alone. Programs coordinating Webb with Atacama Large Millimeter Array will study gas and dust in early galaxies. Programs with Keck telescopes will obtain ultra-high resolution spectra. The data from these future observations will address questions Webb has raised. Are massive early galaxies common or rare? How efficient was early star formation really? When did first black holes form, and how did they grow? What cleared fog during reionization? How quickly did galaxies develop organized structures? Each question requires targeted observations to answer. Beyond specific programs, Webb will continue routine surveys building general catalogues. These serendipitous observations often reveal unexpected phenomena, weird objects that weren't being searched for, rare events captured by chance. Some of Webb's most interesting discoveries might come from analyzing archival data years after observations were taken. Someone looking for one thing notices something strange in background, follows up, discovers something new. The scientific community is committed to making Webb data publicly available. Observations become accessible to all researchers after proprietary period. This democratizes access. Scientists worldwide can analyze Webb data. Small teams at modest institutions can make major discoveries using same data available to large groups at wealthy universities. This openness accelerates progress. Machine learning and artificial intelligence tools are being developed to analyze Webb data. The volume of information is staggering. Millions of galaxies in images, thousands of spectra. Traditional analysis methods can't keep up. Artificial intelligence algorithms can identify interesting objects, classify galaxies, detect anomalies. These tools will enable discoveries impossible through manual analysis alone. Webb's future includes other science beyond cosmology. The telescope studies exoplanets, characterizes their atmospheres, looks for signs of habitability. It observes objects in our own solar system, studies star formation in nearby molecular clouds, maps dust and gas throughout our galaxy. Early universe is just one part of its mission, but its crucial part. The telescope will eventually fail. Some critical component will break beyond repair, or it will run out of fuel for maintaining its orbit. When that day comes, data will remain. Webb's observations will be analyzed and reanalyzed for decades. Future astronomers will mine archives, compare Webb data to observations from next-generation telescopes. Each new telescope reveals things previous ones missed, but earlier data remains valuable for comparisons and long-term studies. The successor to Webb is already being planned. NASA and international partners are designing next-generation space telescopes. Larger mirrors, more sensitive detectors, new capabilities. These future observatories will see farther than Webb, detect fainter objects, provide even more detailed spectra. They will answer questions Webb raises and undoubtedly uncover new mysteries. But that's years away. For now, Webb continues its mission. Every night, when Earth's shadow isn't blocking view, telescope points at distant targets. Light that began traveling billions of years ago crosses final million miles to Webb's mirrors, reflects off gold surfaces, focuses onto detectors, gets converted into digital data, transmitted to Earth, analyzed by scientists, transformed into understanding. The universe revealed its secrets slowly for centuries. Telescopes got bigger, detectors got better, each generation saw farther. Webb represents culmination of this progress. It peers deeper into cosmic history than any previous instrument. What it sees is both familiar and strange. Galaxies forming, stars shining, structure assembling. The processes we expected, but happening faster. Starting earlier, proceeding more efficiently than imagined. The discoveries continue, the mysteries deepen, the answers emerge gradually. So did James Webb kill the Big Bang Theory? The answer is definitively no, but understanding why requires cutting through sensational headlines and examining what actually happened. The confusion arose because some early reports dramatically overstated Webb's findings. Social media amplified the most extreme interpretations. Clickbait articles declared cosmology was broken. The reality is far more nuanced and actually more interesting. Webb discovered that galaxies in the very early universe are more massive more numerous, more organized, and brighter than standard models predicted. This is genuinely surprising. It challenges specific assumptions about how galaxies form and evolve. It forces refinement of detailed astrophysical processes, but it doesn't overturn the Big Bang framework itself. The Big Bang theory rests on multiple independent lines of evidence that remain completely solid. The cosmic microwave background radiation fills all of space with nearly uniform temperature, exactly as predicted if the universe was once hot and dense. The abundances of light elements, like hydrogen, helium, and lithium, match predictions from Big Bang nucleosynthesis with remarkable precision. The expansion of space itself is directly observable through redshifts of distant galaxies. All of these fundamental observations remain valid and unexplained by alternative theories. What Webb really showed is that our models of galaxy formation were incomplete. We underestimated how efficiently gas could turn into stars in the early universe. We didn't fully understand how supermassive black holes could grow so quickly. We didn't appreciate how rapidly some galaxies could organize into stable structures. These are problems with detailed astrophysical processes, not with basic cosmology. Think of it this way. If scientists predicted humans evolved gradually over millions of years, and then discovered evidence that human civilization developed faster than expected, that wouldn't disprove evolution. It would just mean we needed better models of how civilizations form. Similarly, finding galaxies formed faster than predicted doesn't disprove cosmic evolution. It means we need better models of galaxy formation. The distinction between cosmology and astrophysics matters enormously. Cosmology deals with the universe as a whole, its age, composition, expansion, and overall evolution. Astrophysics deals with specific objects and processes within the universe: how stars form, how galaxies grow, how black holes accrete matter. These are different levels of explanation. Webb challenged astrophysical models while confirming cosmological ones. Scientists actually expected Webb to reveal surprises. That's why they built it. Every major new telescope in history has discovered unexpected phenomena. Hubble found dark energy by observing distant supernovae. Nobody predicted that discovery. It revolutionized cosmology, but it didn't invalidate the Big Bang. It added to our understanding. Webb is doing the same thing. It's revealing details about the early universe that previous telescopes couldn't see. Some of those details don't match predictions. That's exactly what should happen when you observe previously hidden regions of cosmic history. The universe is under no obligation to behave exactly as our imperfect models predict. The scientific process is working exactly as it should. Observations contradict predictions. Scientists investigate. They refine theories. They run new simulations. They make better observations. Gradually, understanding improves. This is progress, not crisis. This is science functioning normally. Public confusion arose partly because the initial Webb results were genuinely shocking to astronomers. When scientists express surprise and uncertainty, that can be misinterpreted as the theory being wrong. In reality, surprise is how science advances. If observations always matched predictions perfectly, we wouldn't learn anything new. The lesson from Webb is that the universe is more complex and interesting than we thought. Galaxies can form faster than simple models predict. Black holes can grow ahead of their host galaxies. Reionization can proceed through mechanisms we didn't fully appreciate. These discoveries will drive decades of research. They'll lead to deeper understanding, but they don't require abandoning the Big Bang. The Big Bang theory has now been tested more thoroughly than ever before. Webb has provided observations reaching back to within a few 100 million years of the beginning. The framework holds up remarkably well. The timeline is correct. The expansion is real. The basic story of cosmic evolution is solid. Only the details need adjustment. This is actually more satisfying than if Webb had confirmed everything perfectly. Perfect confirmation would suggest we already understood everything. The surprises Webb revealed show there's still mystery in the cosmos, still discoveries to be made, still questions to answer. That's what makes science exciting. Webb's discoveries have profound implications for how we understand the universe, even though they don't overturn the Big Bang. The implications span multiple areas of astrophysics and cosmology. Each one opens new avenues of research that will occupy scientists for years to come. First, we must fundamentally rethink how efficiently star formation can proceed. For decades, the 10% efficiency seen in modern galaxies was assumed to be relatively universal. Webb shows that assumption was wrong. Early galaxies converted gas to stars much more efficiently. This means something about the early universe enabled processes that are suppressed or impossible today. What changed? The most obvious difference is chemical composition. Modern galaxies contain substantial amounts of heavy elements. These elements affect how gas cools and collapses. They influence stellar winds and radiation pressure. Early galaxies lacked these elements. This pristine composition might have allowed more efficient star formation through mechanisms we're only beginning to understand. Understanding this has practical importance beyond just explaining early galaxies. It affects how we model galaxy evolution throughout cosmic history. It changes our predictions for how many stars formed at different times. It influences estimates of the total stellar mass in the universe. Every calculation that depends on star formation efficiency needs revision. Second, the early growth of supermassive black holes demands new formation mechanisms or dramatically revised growth models. Finding million-mass black holes just a few 100 million years after the Big Bang pushes every known scenario to its limits. Either black holes form much faster than we thought, or they start much larger, or there are growth mechanisms we haven't discovered. This matters for understanding how black holes and galaxies co-evolve. If black holes can get ahead of their galaxies, they might actually drive galaxy formation rather than simply responding to it. The energy black holes pump into their surroundings could trigger or suppress star formation. It could shape how gas flows within galaxies. Black holes might be more central to cosmic structure formation than previously believed. Third, the role of dwarf galaxies in reionization was underestimated. These small galaxies are incredibly numerous and collectively contributed most of the ultraviolet radiation that cleared the cosmic fog. This finding changes how we think about which objects matter for major cosmic transitions. Sometimes the little guys are more important than the giants. This has philosophical implications. It suggests that when studying complex systems, we should pay attention to the numerous small components, not just the obvious large ones. In ecosystems, in societies, in economies, the aggregate effects of many small actors can exceed the influence of a few large ones. The universe teaches this lesson at cosmic scales. Fourth, the ability of some early galaxies to develop organized structures like spiral arms challenges our understanding of how long organization takes to emerge. Spiral galaxies require calm conditions and stable rotation. Finding them in the chaotic early universe suggests order can emerge faster than expected from disorder. This connects to fundamental questions in physics and mathematics. How does complexity arise from simplicity? How quickly can systems self-organize? These questions apply far beyond astronomy. They're relevant to understanding how life originated, how brains develop structure, how cities grow. The universe is a laboratory for studying emergence and organization. Fifth, Webb's observations provide new tests of dark matter and dark energy. The rate at which structure forms depends on dark matter properties. The expansion history depends on dark energy. By precisely measuring when galaxies formed and how massive they became, Webb constrains both. Any proposed modifications to dark matter or dark energy models must reproduce Webb's observations. This matters because dark matter and dark energy remain deeply mysterious. We know they exist through their effects. We don't know what they are. Every new constraint helps narrow the possibilities. Webb's data will be used to test countless theoretical proposals about the nature of these invisible components that dominate cosmic evolution. Sixth, the patchiness of reionization revealed by Webb affects how we interpret observations of the high redshift universe. If some regions cleared earlier than others, then observations of any particular galaxy depend on local conditions, not just cosmic time. This adds complexity but also richness to our understanding. Understanding this patchiness helps explain why different observations sometimes seem contradictory. One galaxy shows signs the fog has cleared, while another, at similar distance, doesn't. Previously, this was puzzling. Now we understand reionization was spatially variable. This resolves apparent contradictions and provides new ways to map how reionization proceeded across space. Finally, Webb demonstrates the power of infrared astronomy. Almost everything surprising Webb discovered was invisible or barely visible to Hubble. Infrared observations revealed hidden populations, dust-obscured objects, and extremely distant sources. This validates the decades of work that went into developing infrared technology and planning Webb's mission. The lesson is clear. To see the invisible, you need the right tools. There are undoubtedly other hidden aspects of the universe that current technology can't detect. Future telescopes, operating at different wavelengths or using different techniques, will reveal their own surprises. Webb's success justifies continued investment in new observational capabilities. These implications collectively paint a picture of a universe that's more dynamic, more complex, and more interesting than previous observations suggested. Webb hasn't broken cosmology, it's enriched it enormously. Despite Webb's incredible observations and the progress scientists have made interpreting them, many mysteries remain. These unsolved puzzles will drive research for decades. Each one represents an opportunity for new discoveries and deeper understanding. The little red dots remain unexplained. Despite intense study, astronomers still don't definitively know what these objects are. Are they extremely compact star-forming galaxies? Dust-shrouded quasars? Some new category of object that doesn't fit existing classifications? Their strange appearance at 600 million years after the Big Bang and disappearance by 2 billion years adds to the mystery. Solving the little red dot puzzle matters because these objects are numerous enough to potentially play a significant role in early cosmic evolution. If they're related to black hole growth or reionization or some other fundamental process, understanding them becomes crucial. Multiple teams are obtaining detailed spectroscopy of these objects. The answer might come soon, or it might require entirely new observations. The exact mechanism for supermassive black hole formation remains unknown. We can observe that these objects exist in the early universe. We can measure their masses, but we don't know how they actually formed. Did stellar mass black holes merge? Did gas clouds collapse directly? Did primordial black holes from the Big Bang serve as seeds? Each possibility has theoretical support, but lacks definitive observational confirmation. This is one of the most fundamental unsolved problems in astrophysics. Black holes are ubiquitous in the universe, yet their origins remain mysterious. Webb is providing crucial constraints by finding black holes at earlier and earlier times. Eventually, these observations should rule out some formation mechanisms and support others. We're not there yet. The discrepancy in star formation efficiency between early and modern galaxies lacks complete explanation. Yes, the early universe was different. Yes, chemical composition matters, but translating these general statements into quantitative models that reproduce observations is challenging. What specifically about pristine gas allows more efficient star formation? What feedback processes were weaker? The details remain unclear. Solving this requires combining observations with sophisticated simulations. Models need to track how individual clouds of primordial gas cool, fragment, and form stars. They need to include radiation pressure, magnetic fields, turbulence, and countless other physical processes. Getting all this right at the necessary level of detail is enormously difficult. Progress is being made, but slowly. The fate of the most massive early galaxies is mysterious. Webb sees them at early times. We see massive galaxies today. Are they the same objects evolved over billions of years? Or did something happen to those early massive galaxies? Did they merge into even larger structures? Did feedback from black holes blow away their gas and halt star formation? Connecting early and late populations is challenging. This question relates to galaxy evolution more broadly. How do galaxies change over cosmic time? What processes drive their transformation from one type to another? Webb provides snapshots at early times. Other telescopes provide snapshots at later times. Connecting the snapshots into coherent evolutionary histories requires careful work. The role of magnetic fields in early galaxy formation is poorly understood. Magnetic fields affect how gas collapses. They can support clouds against gravity or help channel material toward black holes. They influence stellar winds and the structure of accretion disks. But measuring magnetic fields in distant galaxies is extremely difficult. We have theoretical models, but limited observational constraints. Webb can't directly measure magnetic fields, but it can observe phenomena influenced by them. The detailed structures of galaxies, the properties of their stellar populations, the characteristics of their black holes. By comparing observations to models with different magnetic field assumptions, astronomers can indirectly constrain what magnetic fields must have been like. This is indirect and uncertain, but better than nothing. The nature of the densest regions in the early universe remains mysterious. Webb finds occasional galaxies that are extraordinarily massive for their age. These presumably formed in the densest regions where dark matter was most concentrated, but we can't see the dark matter directly. We can only infer its distribution from the galaxies that formed within it. Understanding the relationship between visible and dark matter distributions requires sophisticated modeling. This connects to fundamental questions about dark matter itself. How is it distributed on small scales? Does it clump smoothly, or are there substructures? Can it interact with itself, or only through gravity? Every observation of early galaxies provides constraints on these questions. But the constraints are indirect and depend on assumptions about baryonic physics. The possibility of rare, exotic objects lurking in Webb's data remains open. With millions of sources detected, there's potential for discovering entirely new categories of astronomical objects. Maybe exotic stellar remnants, maybe unusual configurations of matter, maybe phenomena we haven't even imagined. Large surveys often yield surprises when examined carefully. This is one reason why making all Webb data publicly available matters. Thousands of scientists can examine the data from different perspectives. Someone studying one question might accidentally notice something strange that leads to completely different discoveries. Serendipity plays an important role in astronomical research. The more eyes on the data, the more likely rare objects get found. Finally, there's the question of what lies beyond Webb's reach. No matter how sensitive a telescope is, there's always something farther, fainter, or stranger that it can't detect. Webb has pushed our observational frontier dramatically farther than before, but certainly there are interesting objects and phenomena still hidden beyond its capabilities. Future telescopes will reveal them, and they'll undoubtedly bring new surprises and new mysteries. We've journeyed through 13.8 billion years of cosmic history, from the Big Bang to the first stars to the first galaxies. We've seen how James Webb Space Telescope revolutionized our view of the early universe. We've examined claims that it killed the Big Bang theory. Now we can deliver the final verdict. James Webb Space Telescope did not kill the Big Bang theory. It didn't even wound it. The Big Bang framework remains the best explanation for the origin and evolution of the universe. The expansion of space is real. The cosmic microwave background is real. The synthesis of light elements in the first minutes is real. The formation of structure over billions of years is real. All the fundamental pillars of Big Bang cosmology stand firm. What Webb did do is reveal that our Webb provided spectacular discrepancies. Now scientists get to figure out why. The massive early galaxies challenge models of star formation efficiency. They'll lead to better understanding of how pristine gas behaves. The early supermassive black holes challenge formation scenarios. They'll lead to new insights into how these monsters grow. The little red dots challenge classification schemes. They might represent entirely new categories of objects. Every challenge is a chance to learn. This is how science should work. Build models based on available data. Make predictions. Test predictions with new observations. When predictions fail, don't abandon the entire framework. Identify which specific pieces are wrong. Fix those pieces. Make new predictions. Test again. Iterate toward truth. The Big Bang Theory has survived this process repeatedly. It survived the discovery of dark matter. It survived the discovery of dark energy. It survived finding galaxies at higher redshifts than expected. It survived discovering the first stars formed earlier than predicted. Now it's surviving, finding that early galaxies are more massive than anticipated. Each time, the framework accommodates new data. Each time, understanding deepens. Compare this to alternative theories. Tired light, models that try to explain redshift without expansion, fail to explain the cosmic microwave background. Steady-state theories that avoid a beginning contradict light element abundances. Static universe models can't account for the expansion. Every alternative that tries to replace the Big Bang encounters fatal problems. The Big Bang succeeds because it's correct in its essentials, even if details need work. Webb has actually strengthened confidence in the Big Bang by testing it so thoroughly. Before Webb, we could only see back to a certain point. There was always the possibility that going farther would reveal something fundamentally different. Now we've looked almost to the beginning. We see galaxies forming, stars shining, black holes growing. The same physics operates then as now. The story holds together. The sensational headlines that claimed cosmology was broken did a disservice to science. They created confusion. They made people doubt well-established knowledge. They suggested scientists don't know what they're doing. The reality is that scientists were doing exactly what they should. Admitting surprise, investigating carefully, revising models where needed, maintaining the framework where it works. This experience offers lessons beyond astronomy. It shows how science actually functions versus how it's sometimes portrayed. Science isn't about having all answers. It's about asking better questions. It's not about unchanging certainty. It's about updating understanding as new evidence arrives. It's not about individual genius. It's about communities of researchers collaborating and debating and gradually converging on truth. The universe revealed by Webb is more interesting than the universe we predicted. Galaxies form faster than expected. Black holes grow more rapidly than models allowed. Structure emerges sooner than calculations suggested. This means the cosmos is more dynamic, more complex, more worthy of study than we realized. That's exciting. Looking forward, Webb will continue observing for years. Each new dataset will refine understanding further. The spectroscopic campaigns will nail down distances and masses precisely. The time domain studies will reveal variability and transience. The deep fields will find ever more distant objects. Every observation adds detail to the picture. Beyond Webb, future telescopes will push even farther. They'll see the very first stars individually. They'll detect gravitational waves from early black hole mergers. They'll map dark matter distributions directly. Each new capability will reveal new surprises. The process never ends. There's always more to discover. But for now, We can say with confidence what James Webb Space Telescope actually accomplished. It didn't kill the Big Bang theory. It revealed that the early universe was more vibrant, more active, more fascinating than we imagined. It showed that galaxies grew up faster than predicted. It demonstrated that our models needed refinement. It proved that 13.8 billion years after the Big Bang, the universe can still surprise us. The Big Bang happened. The universe expanded from a hot, dense state. Structure formed over billions of years. Galaxies assembled. Stars were born. Planets formed. Life arose. And now, tiny creatures on one small world have built instruments capable of peering back to the cosmic dawn, capable of seeing their own origins, capable of understanding, at least partially, how everything came to be. That's the real story James Webb Space Telescope tells, not the death of a theory, the triumph of human curiosity and ingenuity, the ongoing quest to understand our place in the cosmos. The universe revealed itself to us. We looked, we saw, we wondered, we understood, and the story continues.